Farrell for organizing this workshop in the school. So I'm going to start with giving an overview of the field of antiferromagnetic spintronics. So antiferromagnetic spintronics is the field where you want to make devices in which the active elements of the devices are made of antiferromagnets. So instead of controlling magnetic moments in ferromagnets like you do in the conventional spintronic devices here, what we're trying to do is to make an equally efficient control of antiferromagnetic moments, and eventually try to do it in a way that will be compatible with conventional microelectronics or optoelectronics. So as Aaron mentioned, this is a relatively new field, but there are already a few review articles. If you want to read something about the early theoretical proposals, then these are these two first papers. And the more recent theoretical proposals, but also some experimental realizations of these ideas are reviewed in these latter two review articles. So when we talk about spintronics, I think it's always good to start by noticing that spintronics is a field which is very closely tied to magnetic recording. In fact, magnetic recording is the main area where people are thinking of applying the ideas that come out from spintronics research. And so let's start with a very brief overview of the field of magnetic recording. It started at the end of the 19th century where people were trying to record sound. And you are definitely familiar with gramophones, and what I was surprised myself is that the first magnetic recorders were manufactured pretty much at the same time as gramophones, so at the end of the 19th century. It's no wonder then that the basics for the recording, that means how you write at that time sound into the magnetic wire and how you read it back, it had to be based on the 19th century physics, which means that for writing you would use a Hershey magnet generating a magnetic field, and that magnetic field would reverse magnetic moments in the magnetic domains on the wire. And reversely, when you want to read it electrically, these moving magnetic domains would generate an electric field on the same magnet. Well, magnetic wire recorders were very unsuccessful technology. Gramophones were really covering the whole field of sound recording until the 1930s, where people invented tape recorders. It was a much more practical device, having magnetic media on a plastic tape. And at that time, it really became a major technology for recording sound, eventually video, and now data. And tapes are still around for storing large amounts of data. But of course, later on in the 50s, people came up with new concepts. One was the hard disk drive, which obviously is a very common technology until these days. And they also invented the first solid-state memories. That means people were recording information into a device where there was no moving part. So it started in the 19th century, and still magnetic recording represents one of the major technologies for storing data. It's mostly due to magnetic recording that we can store every second 1 hour or we can upload every second 1 hour video, for example, on YouTube. But without moving from the 19th century into more modern physics principles for magnetic recording, this most likely would not be possible. And this is where spintronics comes into play. Spintronics is basically a combination of new phenomena that have been discovered in the 20th century, in particular when we talk about hard disk drives, the giant magnetoresistance or tunnel magnetoresistance phenomena for reading the information, and combining it with magnetic recording technology. This is the field that we now call, let's say, applied spintronics. Well, when I say that magnetic recording is a keeper, we should, at this point, also put a question mark when we make this statement, because there are some major competitors when we're talking about storing data, and these are semiconductor memory. The semiconductor memories, we have several versions. We have flash, which is basically storage medium. It's relatively slow, but it can store more and more data. And in particular for mobile technologies, this is becoming a major competitor for hard drive. And of course, we have then the random access memories in computers, which are also, this area is completely dominated by semiconductor memories. So Spintronics is also trying to enter this area of memory chips. And it has to be, in my opinion, it has to be successful in order to really keep magnetic recording technology at the forefront of information storage and memories. And to do this, it's very likely that the phenomena that has been discovered in the 20th century would not be enough for Spintronics to stay alive. Well, we need to keep on coming up with new ideas, new phenomena, and some of them have already been discovered in the beginning of the 21st century. Now, all the spintronic applications, all the magnetic recording is based on ferromagnets. So what about antiferromagnets? This workshop is going to be about antiferromagnets. So how are antiferromagnets related to the magnetic recording? Where are they? Well, surprisingly, or maybe not surprisingly, at the time where magnetic recording became the major technology, at that time physicists came up with the final classification of the main classes of magnetic materials, in particular due to Louis Nails, who basically said if you have a material with spins, then you can have three canonical types, if you will, of behavior of these spins. In one case, materials that are called paramagnets, when you look at the magnetic susceptibility, that means the ability of the spins to be aligned by applying external magnetic fields. And you look at that susceptibility when decreasing the temperature, it increases. So it becomes easier and easier to align the spins with external magnetic field. However, whenever you remove the magnetic field, the order is gone. Then you have the ferromagnetic materials, and the ferromagnetic materials at high enough temperature behave the same as paramagnets. However, at some critical temperature, there is a spontaneous order. So it means that it takes an infinitesimally small magnetic field to fully align the magnetic moments. There is a spontaneous order. And then, and this was the greatest puzzle which was solved eventually by Louis Nail, there were materials which also behaved like paramagnets at high enough temperature. So there clearly were spins, there were magnetic moments, and you were able to align those magnetic moments in the magnetic field. However, after some critical temperature, it looked as if the moments disappeared from the material. And Louis Nail explained that it was not that the spins left the room, but they arranged in a different way than in ferromagnets, in a way that the neighboring moments would align anti-parallel, and it appeared as if the moments disappeared. Now, from the perspective of magnetic recording, it's obviously the ferromagnets that are the favorable materials, because you have means how to control them very easily by external magnetic field, and because of the magnetic order, you have the memory functionality, and that's the key for recording. Well, paramagnets were not considered useful for this because there is no spontaneous order, so you cannot realize the memory functionality. With antiferromagnets, there is no spontaneous net moment. There is a magnetic order, but there is no net moment, so it's then very difficult to control antiferromagnets by external magnetic fields, for example. So you don't have the control over them, so again, they were assumed to be not useful for magnetic recording. Not only in the 1930s, but in the 1970s, where Louis Nail got his Nobel Prize, he still quoted that or mentioned that these are very interesting, peculiar material, maybe from the theory perspective, but from the application perspective, they're completely useless because of the lack of control. Well, I think we're very fortunate that we live in the 21st century, that we have some new phenomena that were not known in the Louis Nail's times, and suddenly the game is completely different. It has changed. First, it started with phenomena that have been discovered in paramagnetic materials or non-magnetic materials that turns out to be very useful for, potentially very useful for magnetic reporting. And the two, let's say, prototype phenomena are the spin Hall effect and the inverse spin galvanic or Edelstein effect. So spin Hall effect is that you take a non-magnetic system, a paramagnet, you run electric current through it, and what happens due to the direct coupling between the linear momentum and the spin angular momentum of the electron, that spin up electrons are deflected towards one edge of your conducting strip, and the spin down electrons towards the other edge. So what you can have at this edge is a spin accumulation or spin polarization. Now in the spin galvanic effect, what happens is that you again run electrical current through the system, but now you generate a non-equilibrium spin polarization, but not at the edges of your conducting wire, but throughout the entire bulk of the system. The entire bulk of the system now becomes spin polarized. Now these phenomena have been discovered simultaneously as companion phenomena in the same types of semiconducting materials in 2004 by several groups. There was a group in Santa Barbara that discovered the spin Hall effect, two groups in Germany that discovered the inverse spin galvanic effect, and there was one group in Cambridge here at Wunderlich who in fact discovered both phenomena simultaneously in the same experiment. So let me take a closer look at this experiment because it's been very useful later on for developing the field. First of all, I said it showed that these two phenomena can be present simultaneously. So it's in the same devices fabricated from the same p-type gallium arsenide. P-type is very useful because the valence band of the semiconductor has strong spin-orbital coupling. And so in this experiment, what was done is that there was an electrical current, and because in the inverse spin galvanic effect, you're looking at the bulk spin polarization throughout the entire cross-section of your wire, there is a light-emitting diode, and through the polarization of the light that is emitting from this light-emitting diode, you can see what is the polarization of the carriers that carry the electrical current. And indeed, in this experiment, what was observed that there is a non-zero spin polarization when you run electrical current, even at zero magnetic field. And the observation angle was in plane, so the polarization of the carriers was also in the plane. What you also notice here is that the spin polarization that you generate is comparable to generating equivalent spin polarization in the material by fields of several Tesla. Now, the spin Hall effect, you have to just change a little bit the geometry, you run electrical current, and now what you're supposed to look is the edge spin polarization, which should have opposite sign on these two opposite edges, and should be pointing out of the plane. And here is the experimental observation that indeed in the out-of-plane observation angle here, you see opposite spin polarization at the opposite edges. And when you recalculate what is the degree of spin polarization, it can reach 1 or even 10%. Again, a polarization for which you would normally need 1 to 10 Tesla magnet. So I just pull out a very, very old slide. As you see, it's a very old slide. The paper is already almost gone, and the letters are almost invisible. So this was one of the slides that we were preparing after the very early demonstration of the spin Hall effect. And what I just want to point out here is the title here, The Power of Spintronics. I think we were all overwhelmed by the strength of the phenomenon that you can generate equivalent spin polarization in a microchip by microamp current, as you would normally do with a 100 amp current running through a big superconducting magnet. So we felt like the Dirac was beating Maxwell by a big margin here. So it looked like a very, very large, amazingly large effect. But you should also read this line here. This is still from the original slide. Need to learn much more to fully exploit spin in microelectronics. So translated into normal words, it means we have absolutely no idea what this phenomenon can be used for. Well, it didn't take too long for other groups to figure out that these type of phenomena where you generate in paramagnet spins by just running weak electrical currents can be used for magnetic recording. You can do it in the spin Hall geometry, where you run this electrical current in a paramagnet, you accumulate those spins at the interface, and those spins then interact with the magnetic moment of the ferromagnet on top, and they can switch it. Two groups worked on this initially, the group in Spintac and in Barcelona, and also the group in Cornell here. I was at a meeting just a week ago where Bob Burman was talking about this experiment, and he was mentioning that he was explicitly discouraging the student from doing this experiment because he thought that there's no way that a paramagnet can switch a paramagnet. So fortunately, the student was not listening to them, and he still did the experiment, and it turned out that you can indeed switch it. Now, so this was in the 2011 and 12. A couple years before, the inverse spin galvanic effect was shown that it can switch a ferromagnet. In this case, it was a straightforward generalization of the p-type gallium arsenide. The only difference here is that now the p-type gallium arsenide is ferromagnetic in equilibrium by doping it with sufficient amount of manganese. So you have equilibrium moments, you run electrical current, this electrical current then generates non-equilibrium spin polarization, which can be misaligned with the equilibrium magnetization, and again it can exert the torque and it can switch it. So, well, maybe there's another lesson to students here, is that this effect was discovered before this one, but in fact it was these experiments that really caught the attention, and the very reason is that this is a low Curie temperature material, and only a few people in the world were able to grow it. So I guess the lesson is, if you want to discover a new phenomenon, just discover it in a material that everyone has in its drawer, because then you can draw a lot of attention, and not just a material where only a few nerds can grow it. So what about antiferromagnets? What implication do we have from can we get for antiferromagnets? Well, the problem with antiferromagnets is that we have these alternating magnetic moments in the ground state or in equilibrium. So if we want to have an efficient control, equally efficient as we have in ferromagnets, we do not need, or we do not, the requirement is not to generate a uniform magnetic field or effective field from this Dirac equation, but we need to generate a field which alternates from one atomic site to the other, as if you had to wind a coil in a way that one coil will generate magnetic field pointing in one direction and the neighboring pointing in the opposite direction. So doing this literally by winding the coils is impossible. It's a science fiction, because you have to imagine that you have millions to billions of these magnetic atoms in one recording bit cell. So you have to come up with another realization of this to generate an effective field of the same property, but not a real magnetic field. And here we can use this Dirac equation, this spin-orbit coupling phenomenon. We use the same type of phenomenon as was the one that generated the current-induced switch in the gallium manganese arsenide. The reason why electrical current can generate non-equilibrium spin polarization is this Dirac equation. But on top of this, you need to have some symmetry requirement, and that symmetry requirement is that the unit cell in the bulk crystal does not have an inversion symmetry. Only in that case you can generate non-equilibrium spin polarization in the entire bulk. In the spin Hall effect, on the other hand, you can have a crystal which is inversion symmetric, because the polarization is only at the edges, and the edges always break inversion symmetry. But if you want to have it in a bulk, you have to have a crystal that breaks inversion symmetry in bulk. So that's what happens in gallium arsenide, because in Zeeland lattice, there are two atoms which are different elements. This is gallium and this is arsenic, and this breaks the inversion symmetry of the Zeeland lattice. However, if you go one step back to the diamond lattice of silicon, for example, or germanium, you look at that point, this is an inversion center of the lattice, because now the sites A and B are occupied by the same element, for example, by silicon. So the diamond lattice has an inversion symmetry, however, it still has two atoms per unit cell. The site A and site B are different, are not equivalent, because from site A, I'm going downwards, I need an atom. But when I go upwards, that means going through this direction, there is an empty space. Atom B, I go upwards, there's a neighboring atom, I go downwards, there's an empty space. So the sites are locally non-central symmetric, they are in fact inversion partners. So now when you run electrical current, you generate opposite spin polarizations at these two sites.
And meaning opposite non-equilibrium spin polarization is something like generating an effective magnetic field that changes sign when you go from one atomic side to the other. So that's precisely what you need to have an efficient, effective field that can switch an antiferromagnet, and that's something that has been demonstrated theoretically and also experimentally in this material, copper manganese arsenide. It's not an accident that it's a similar material to gallium manganese arsenide. We just replaced one element, gallium with copper. It's because you can then easily grow it in the similar system, but also you can expect that the effect will be strong enough because it's been already strong enough in this material where you have similar types of carriers in the system. So it's been demonstrated in experiments, but not only in the laboratory. It's been shown soon after that you can implement these antiferromagnetic electrically switchable bits in a simple Arduino-based printed circuit board. You can plug it through USB to a computer, and even theorists like myself can start doing experiments in the kitchen. Well, what's remarkable is that this is indeed an antiferromagnet. You can try to put this chip into 12 Tesla magnet, not the entire printed circuit board. It probably would not fit, but just the chip. And still you can switch it. Still you can write zeros and one in the system. And very recently, it's been shown that you can go down to 250 picosecond timescales for writing the information. So with that, we're at the position that we can start thinking of developing a new direction of spintronics in which, similar to ferromagnets, you have magnetic recording which is based on spin. So ultimately, it could be radiation hard. It would be non-volatile because it's based on ordered spins, like in ferromagnets, and antiferromagnets are also ordered. But now we can have many advantages compared to ferromagnets. Because there is no net moment, there is no dipolar fields, and we have other means to control the spins instead of using magnetic field. So we can take advantage of this, that they will be insensitive, invisible to magnetic fields. There won't be any magnetic crosstalks between the antiferromagnetic bits. And as already indicated by these fast switching experiments, ultimately, antiferromagnets, their internal dynamics is in terahertz compared to the gigahertz in ferromagnets. So the limits for the speed for switching are 2, maybe 3 orders of magnitude higher than in ferromagnets. But we're not there yet by having real applications. Certainly still, the applied spintronics is driven by ferromagnets. We all know here in this audience that eventually it must be antiferromagnets that will be ruling the world of magnetic recording, but so far we're not there yet. So we should stay, let's say, friendly to the other community that is still dealing with ferromagnets for some reason. And one way how to do this is to use antiferromagnets in a way that they would help ferromagnetic spintronics. Well, in fact, antiferromagnets have been around the ferromagnetic spintronics from the very beginning. For example, the real crystal antiferromagnets have been and are still used as materials that fix or help to fix the moments in the reference ferromagnet in this tunnel magnetoresistance device, which is the basis for the ferromagnetic MRAMs. Also, the top, the recording ferromagnet, is usually formed in a geometry where there's another ferromagnet on top of it, and there's a weak antiferromagnetic coupling between those. And the reason for this is one way how to get rid of the problem of the stray fields, the unintentional crosstalks that you create these synthetic antiferromagnets. It also turns out that you can have a much more deterministic switching if you have this weakly coupled, antiferromagnetically coupled layers. But now people are, in much more recent research, are trying to use this synthetic antiferromagnet. So these are real ferromagnetic films, but they have an antiferromagnetic coupling. When this antiferromagnetic coupling is becoming stronger, you can achieve a much higher domain wall velocities than in just a single ferromagnetic film. And the reason for that is that when you look at the domain wall, the problem with running a domain wall at high speed in a ferromagnet is that once you start applying the driving field, which could be current or external magnetic field, your spins start to tilt away from the plane of the domain wall. So you're starting to push the domain wall. By doing this, you are deforming the domain wall. And if you overdo it, you basically break the internal structure of the domain wall, it becomes unstable, and that slows down the motion. But if you have this synthetic antiferromagnet, when you are trying to push your spins away from the plane of the domain wall, simultaneously you are canting the moments in the synthetic antiferromagnets. They want to be antiparallel, but you're trying to push them into the parallel configuration. And they want to avoid it. And that's why this so-called Walker breakdown is delayed. You require higher fields or higher currents to achieve it. So in that case, you can increase the velocity from the typical 100 nanometers per nanosecond into thousands of nanometers per nanosecond. Now, ultimately, these synthetic antiferromagnets have antiferromagnetic coupling, which is stronger than these, let's say, first toggle MRAMs, but still, it cannot be as strong as the antiferromagnetic coupling in a crystal antiferromagnet. It's still about 2 orders of magnitude weaker. And what it means is that if you had a domain wall in a real crystal antiferromagnet, then there would be not just delaying the Walker breakdown, there would be no way how by meaningful or reasonable external fields or currents you could really achieve the Walker breakdown, meaning turning the central part of the domain wall from an antiferromagnetic coupling to a ferromagnetic coupling. In a synthetic antiferromagnet where this coupling is weaker, it's still possible, but in an antiferromagnet, it's close to impossible. And that means that you completely remove the Walker breakdown, and you can, at least in theory, the limit for the domain wall velocity speed is another order or maybe 2 orders of magnitude higher. So now when we talk about elements that would be 100 nanometers in size, you can switch those elements by domain wall motion, not on the time scale of nanoseconds, but on the time scale of picoseconds. Well, another way how antiferromagnets can potentially help the ferromagnetic spintronics is shown in this transparency. So we talked about already, or introduced already this experiment. This was the experiment where a paramagnet, in particular platinum, and the spin Hall effect in paramagnet was responsible for switching the reporting ferromagnet, in this particular case, cobalt. Now, in this experimental geometry, the cobalt is out of plane polarized, and we're switching it from out of plane in one direction to the out of plane opposite direction always. When you do this with the in-plane electrical current and with the spin Hall effect, the problem is that in this geometry, the spin polarization is in the plane, and it does not determine whether the up or down pointing moments are the stable ones. As you see, there is no way how to distinguish which of them is preferred by the spin Hall effect. So you can start dynamics, you can induce torques, but the switching is not deterministic. If you want to make it deterministic, you have to apply an additional in-plane field, which then just shows you that one of these 2 states, by running an electrical current in one specific direction, would be the stable one. And when you reverse the current, the other state will be the stable one. But to break the symmetry, you need to apply in-plane magnetic field, and that's indeed how these experiments were done. But having an external magnetic field applied during your switching is an additional complication, which you definitely want to avoid in a real magnetic random access memory device. So one way how people are trying to avoid this is to replace this paramagnetic platinum with an antiferromagnetic spin Hall generator. In this particular case, it's a platinum manganese. So it's an antiferromagnet, but antiferromagnet can also generate spin Hall effect, just like paramagnet. And in fact, it can generate a very strong spin Hall effect that can generate switching of the adjacent ferromagnetic reporting film. But there's an additional feature at this interface. This additional feature, I already mentioned it, this was the way how the antiferromagnet can pin the ferromagnet. This is this exchange coupling in this interface. And if this exchange coupling is not strong enough that it completely pins the ferromagnet, but it's still there, it produces some sort of an in-plane magnetic field which breaks the symmetry the same way as applying an external in-plane magnetic field. So now, without having to generate the magnetic field externally, if your spin Hall generating layer is an antiferromagnet which produces this exchange biasing field, it can replace the symmetry breaking field, and you can have a deterministic switching, as been shown in these two papers here, without any external magnetic field. Other ways how antiferromagnets can be supporting ferromagnets is that you now use an antiferromagnet. The proposals are in particular insulating antiferromagnet as a very efficient means for transmitting spins from, let's say, a ferromagnetic injector into a ferromagnetic collector in devices where you want to transport spin over long distances. There are proposals and also some first experimental demonstrations that spin information or spin polarized currents can be transmitted through an antiferromagnet in a very efficient way over long distances. And finally, you can use an antiferromagnet when you drive the antiferromagnet out of equilibrium, for example, by doing a resonance experiment or by just applying a heat gradient, that you can use antiferromagnet as a generator of spin current that can then be used in paramagnets or in ferromagnets in the other parts of the spintronic device. Now, if antiferromagnets can be helpful for ferromagnetic spintronics, how about vice versa? Maybe ferromagnets can be also help understanding or developing antiferromagnetic spintronics. Obviously, ultimately, we want to have devices which completely avoid ferromagnets because we don't want to have all the problems with ferromagnets, stray fields, sensitivity to field perturbation, etc. But at the beginning, it turned out that it's very useful to still have a ferromagnet in your experimental device that will assist your antiferromagnetic spintronic functionalities. There are two examples where having a ferromagnet was very useful to first demonstrate the electrical readout in an antiferromagnet. The first example, it was just a simple ohmic device where there was a piece of antiferromagnet iron rhodium, and there is a demonstration that you can read the direction of the antiferromagnetic moments from perpendicular to parallel with respect to the applied electrical current by an anisotropic magnetoresistance. But at that time, people did not know how to efficiently switch the antiferromagnet. We want to try to read it electrically, but if you want to read it, first you have to have means how to rearrange the antiferromagnetic moments. And here the magic was that iron rhodium is an antiferromagnet at room temperature. However, when you boil it, when you increase the temperature by 100 degrees, it develops a ferromagnetic order. A few materials can do these tricks. Once you have a ferromagnetic order, then you can apply a weak magnetic field. You can reorient it in whichever way you want. And then you cool it down to room temperature, it becomes an antiferromagnet, but with a defined direction of antiferromagnetic moments. So ferromagnetism helps antiferromagnetic component in the right way. Another realization of a similar concept is now iridium manganese is also an antiferromagnet, antiferromagnetic metal, but it does not have this transition into a ferromagnet. So instead, you attach a ferromagnet underneath, and you use again this exchange coupling in the interface. Magnetic field couples to the ferromagnet. This exchange coupling then helps reorienting the antiferromagnet together with the switching of the moments in the ferromagnet. And then in a tunneling device, you can read out the electrical resistance, how that changes when you change the direction of antiferromagnetic moments in this system. And one of the surprising and very encouraging results was that in this tunneling structure, you can have fairly large magnetoresistance signal exceeding 100%. Now, one of the merits of antiferromagnetic spintronics that I already emphasized is that the internal frequency of dynamics in antiferromagnets is in terahertz. Has that been already demonstrated? Oh yes, it's been demonstrated some time ago, maybe from, we can go 10 years back, where people starting to do experiments in insulating antiferromagnets, and these experiments are optical. The advantage of optical experiments is that you can excite them on the time scales comparable to the dynamics, but you can also do real-time measurement of the dynamics. You can visualize what the moments are doing on the time scales of picoseconds, which would be obviously extremely difficult, if not impossible, electrically. And so these are just two types of experiments. One experiment is where you just hit it with an optical pump. Basically, you heat the system of your antiferromagnet, you disturb it from the equilibrium ground state into some excited state, and then you induce dynamics. And what is seen here that indeed the dynamics, when you look at the time scale of these oscillations, they are in the picoseconds. So that just confirms the terahertz internal frequency. Well, if it's in terahertz, then it's a very good idea. Instead of trying to excite it with an optical pulse, you just excite it with a terahertz pulse. Because if the internal dynamics resonance frequency is in terahertz, it should be very susceptible to terahertz excitation. And so this is exactly this type of experiment where the nickel oxide insulating antiferromagnet was excited by terahertz, and then it was measured again by light in real time. You can see the oscillations, and again they're in the picosecond time scale. So all these experiments have been done on insulating antiferromagnets, so it looks like there is a gap from the optical studies of antiferromagnets where you start to exploit the high frequency of these systems and the spintronics, which requires normally conductive materials. Because you want to try to build an electronic or microelectronic device. Well, very recently there's been an experiment.
Maybe just a small comment.
Okay.
On the left experiment that you're showing, there is no heating. Excitation is fluid transparency here. So you mentioned that the laser pulse hits the system, but there is no heating.
You're right. And it's this process.
Yeah, exactly. And this fully femtosecond is not picosecond. Here we have 20 terahertz magnet.
Yep. Thank you. There's been other experiments where it was because of heat, early experiments, but you're right, that in these experiments it is 2M excitation. Thank you for clarification. So here, as I said, these two experiments, and there were many other experiments, they were done dominantly on insulating antiferromagnets. But very recently, there is a report where in a conductive, in a metallic antiferromagnet, it's the very same antiferromagnet where the electrical switching was demonstrated in copper manganese arsenide. It was possible to show that you can not only excite it, in this particular case, it's emitting the antiferromagnet, but you can also detect it optically in real time through magnetooptical effect. It seems to be one of the first demonstrations or realizations of optical readout of a metallic antiferromagnet, which may be very important because all the knowledge that is being around in the community of optical excitation and detection of antiferromagnets and insulators, maybe we can now use it in metallic antiferromagnets, so we now have the bridge from the electronic device into the or spintronic devices into the opto-spintronic devices. If we now think of maybe even more exotic directions of research in antiferromagnetic spintronics, where antiferromagnets would play a very unique role, unparalleled in any other magnetic systems. So one example that will be discussed again during this workshop is the connection between Dirac fermions, that means relativistic quasi-particles in condensed matter systems, and magnetism. Well, the Dirac fermions you're definitely very familiar with, started with the discovery of the singulary sheet of graphene, which hosts these Dirac cones. So basically, in a laboratory environment, you can generate Dirac particles like neutrinos of similar properties that would be known from particle physics. So this has been a fascinating discovery, and it developed into an entire field of topological insulators, semimetals, and eventually superconductors. Now, one thing that seems to be quite difficult within that field of these topological systems and Dirac quasi-particles is to find means how you can efficiently manipulate those Dirac quasi-particles. Because they are typically defined by the symmetry of the crystal, and so you have to do something very substantial to the crystal to efficiently manipulate the properties of these Dirac particles. But now look at what we need basically to have these processings. One of the key requirements is to have two sites in a unit cell. Graphene is a perfect example where you have the honeycomb lattice with the site A and site B. And if you have two sites, then there's a good hope that there will be two bands somewhere in the band structure, and those bands will cross. And this is what then can create these Dirac quasi-particles. Now, if you recall, in our antiferromagnet, where people demonstrated the efficient electrical switching, it was precisely the same requirement. We had to have 2 sites per unit cell in order to generate this effective magnetic field that alternates from one side to the other. And these sites had to be these inversion partner sites, something which looks exactly the same as in graphene lattice. Now, to have these crossings protected, we know that you should have a symmetry, inversion symmetry in the unit cell and time reversal symmetry. And that was a problem for trying to find these systems in magnetic materials, because ferromagnets break time reversal symmetry. However, in this lattice, you have a broken time reversal. You also have eventually broken inversion symmetry, because the moments break this inversion symmetry. However, the combined symmetry, inversion and time reversal, is conserved. And it's precisely this symmetry which allows you to have these efficient current-induced torques and switchings in the antiferromagnet. And PT symmetry, the combined symmetry, is enough for protecting these degeneracies or the direct points. So the physics that was needed for the electrical switching suddenly seems to be precisely the same physics to realizing the direct particles and to having the protected crossings of them, which at least to me sounds like a completely serendipitous coincidence. I would have never noticed or realized that, but because of a brilliant student, Libor Schmeichel, we now have an idea that these 2 worlds may be connected. But not just that, by now reorienting the magnetic moments, you can start to manipulate these direct crossings. So you have a way how, via magnetic order, you can control without deforming your lattice or changing the lattice. You can deform these direct quasi-particles. Another example of interesting, to me at least, coincidences, for some other people definitely something that they have foreseen, is if you look at fermions. One of the problems with ferromagnetic fermions is when you try to move these guys, they will tend to deflect to one side, because they have this topological number, and because of this topological number, there is a Magnus force that tends to deflect them. However, if you would have antiferromagnetic fermions, the 2 opposite topological numbers of the 2 opposite spin sublattices would cancel out in this Magnus force, so the antiferromagnetic fermions will tend to go in a straight line, as has been recently predicted theoretically. So these have been just 2 examples of maybe more exotic but very unique features of antiferromagnets for spintronics. But let me finish with one feature, again, from my perspective, unexpected, unpredicted, but which maybe puts us back down to earth for something that may find practical applications in the near future. And that is a multi-stability of these antiferromagnetic bit cells. It's not that you can just realize zeros and ones when you try to write these bit cells electrically. You can write pulses, let's say, in one direction, but successively along the same current path, which would, for example, favor this antiferromagnetic moment orientation. But you can do it several times in one direction, and only then several times in this orthogonal direction, and you will write these lower resistance states. But you can write many of them, and they seem to be equally stable, and they seem to also be well-defined. So the whole thing is very reproducible. So instead of having only 1 bit per cell, so only 0 and 1, you can have multiple bits which can be stored in the same cell. And it's not just 3 here and 3 there. You can in fact do an experiment where you have several hundreds of metastable states, and maybe a couple when you pulse in the orthogonal direction, and again several hundreds. So you can place all these tricks. You can do this on millisecond pulses. You can do this in a laboratory. You can do this microsecond pulses on this USB device. But if you take the fastest pulser you have available, which can generate 250 picosecond pulses, you see that you can now start to realize something like a pulse counter, where you would hit your system with, let's say, 1 pulse, look at the state, 2 pulses, 100 pulses, 400 pulses, even 1,000 pulses, and you see perfectly distinct states of the memory, which are non-volatile states of the memory. So you can not only realize a memory functionality, but that bit cell also can provide with some first logic functionality, for example, counting pulses. Now, this multiple stability seems to be not a unique feature of one particular antiferromagnet. It's connected to the multi-domain structure of antiferromagnets which do not suffer from these stray fields and seems to be common. This multi-level stability has been observed in an antiferromagnetic semiconductor, mainly telluride, but seems to be also responsible for the multi-level stability of this device that I already introduced as the spin Hall switching over cobalt. We're looking at the cobalt response, which is multiple stable, but due to the antiferromagnet underneath. So, to summarize, at the very beginning, we could have anticipated that if we can control efficiently antiferromagnets, we would have another radiation-hard, non-volatile means how to record information. But on top of that, we have some additional merits compared to ferromagnets corresponding to the no net magnetic moments and no dipole fields and the terahertz dynamics limits. But I also showed you that there are many things that are maybe less expected. That we can combine now two fields of spintronics and magnetism and the topological states in condensed matter. We can see antiferromagnets in many types of materials, insulators, semiconductors, semimetals, metals, or even superconductors, fermions, or other textures, spin textures might have very interesting features. And this multi-level stability seems to be intrinsic to antiferromagnets and can lead to some interesting applications, maybe even in the near future. So, thank you very much.
I've just seen a very rapid overview. Just to inform you, of course, that all of the talks here are taped. Will all be in the YouTube channel, which I hope you all subscribe to it, the SPICE YouTube channel, as well as the slides. So, you know, it was rapid, but you can review it again. So, questions maybe before the break? 1 or 2 questions. Yeah.
You mentioned briefly when you were showing optical experiment that you recently reported an optical experiment of copper manganese arsenide. Can you please tell us more or less what could you do in that material with an optical pump?
So first of all, there are the experts who did these experiments in the audience. So I will then point you to the experts. Peter Unitz is sitting there. But I can tell you quickly, in this experiment, what he was trying to identify optically was the position of the easy axis, or if you want, the direction of the antiferromagnetic moments, which normally you have to go to neutrons, or you have to go to synchrotron facility to do X-ray magnetic linear diaphorism. So what they showed in their lab that you can do optical magnetic linear diaphorism measurements, where he was just hitting it with a pump laser. It was disturbing the system, and then looking at the response in the NLD, and from that response he was identifying by changing the plane of the polarization of the probe pulse, where are the antiferromagnetic moments. So it was used to make a tabletop optical experiment of determining the easy axis in this antiferromagnet, which is a highly non-trivial thing in an antiferromagnet.
So the pump heats up, and you are only putting on dynamics,
Yeah.
no switching.
Yeah, there was no switching there.
Questions from students?
Yeah, the question has been bothering me for a long time and still following me. So the most impressive result that you've shown on coordinating after antiferromagnets. So do you have any good feeling about what could be, how general are those results? If you think about non-coordinating antiferromagnets, that non-coordinating antiferromagnet could be useful, or and if so, how?
So, one of the first really encouraging experiments, at least to us, was this demonstration of the large tunneling and isotopic magnetoresistance, which was in iridium manganese. Iridium manganese is a non-collinear antiferromagnet. So this is one example where already from the very beginning, this was not because it was intentionally chosen to be non-collinear, but just because NRAM people who grew this stack were used to grow iridium manganese nickel iron or permanent interface, but in the other, obviously in the other order. So it shows that yes, you can have large magnetoresistance in non-collinear antiferromagnets, and again, there's been theory, maybe not yet published, but should be published soon, trying to look at the anisotropic magnetic resistance and in non-collinear antiferromagnets, which is not immediately obvious how it should work, but it works, and it can be equally strong as in collinear ones. There are other people that are looking into dynamics in non-collinear antiferromagnets and the differences between collinear and non-collinear, how the torques would work on non-collinear. So there are complications, it's more complex, but still it seems to be equally feasible to do these and realize these phenomena in non-collinear antiferromagnets. And I think they're going to be just richer. Some of the things may be richer than the collinear ones. So that's another difference, which I did not emphasize between antiferromagnets and ferromagnets. Ferromagnetic ground state, there is one ferromagnetic ground state. But when you talk about antiferromagnetic ground state, even with collinear ones, you can have multiple types of arrangements in a collinear one, and when it comes into a non-collinear, you can have 3 sublattices, 4 sublattices. So it becomes much richer also from that perspective.
With that, let's thank Tomas again for one tutorial.